Hello there. I'm here today to talk to you about some falling objects, and we asked our friend here to stop by just to make sure we didn't do anything wrong. So we're going to drop this tennis ball and watch how the energy changes. So up at our height where we start, we have the most potential energy we can ever have. And as the ball falls in the middle point, close to the middle point, we have equal kinetic and potential energy. Right before it hits the ground, we have the smallest value of potential energy approaching zero, approaching the limit of zero, and the most amount of kinetic energy. As the ball hits the ground, there's some energy transferred into the ground, but this ball also is a spring and has spring energy. So the energy is conserved in that way, and that's why it bounces back up.
Transfer and transform.
Transfer and transform. Yes. We're transferring energy to the ground, and we're transforming the kinetic into spring, which is potential, and then back to kinetic when it bounces back up. So, one more time. So, it looks like we're actually conserving about half the energy, and the rest we're losing into the ground and air resistance.
Now for the other ball.
Okay. This, thank you, sir.
Yeah, celebrity.
Just get another shot of our friend.
Okay, I'm gonna zoom in on the friend here.
Yeah.
Oh yeah. Yeah.
Take a look at this equation up here.
Oh, I got the equation in there. Is that E equals MC squared?
Yes, it is.
Ah. Okay, zoom back out.
Energy, mass, and the speed of light squared.
Oh, nice. Okay, now.
So this is another ball.
Close up, close up, close up.
Let me back up here and get closer to our buddy.
Yeah.
Okay, so
should you re-enter for this one?
yeah, re-enter. Okay.
Well, no, now.
Today I'm going to talk to you about this ball, much smaller, more dense, compared to this one. This doesn't have quite the same spring capability, so I'll drop this for you here. Yeah. Okay, so up here at our height, maximum height, that is our maximum potential from gravity. As it falls, we're going to hit an equilibrium point in the middle, where we have equal potential and kinetic energy. Right before we hit the ground, we have maximum kinetic and almost zero potential. And what's different about this ball is that it does not have the capability of having a lot of spring energy, the potential of a spring. So most of the energy is just transferred into the ground. And that's why the energy is not conserved well, and why it only bounces a little bit. So that is and there's also air resistance. Wow. So the energy is transformed from potential to kinetic, and then some is transformed into potential again in the form of a very small amount of spring energy, but most of it is transferred to the ground.
Good.
Why, hello. I didn't see you come in there. To answer part B, the reason they don't bounce to the same height is because the metal ball transfers most of its energy into the ground, while the tennis ball transfers most of its energy into spring energy once it hits the ground. Potential spring energy.
Which then transforms into kinetic.
Which then transforms into kinetic. Thank you.
Have a nice day.
Thank you. Good evening.
The question I just answered was part C, not part B.
120 AC. Seems to be this outlet's working okay.
Volts.
Fuck! No! 120 volts AC. Seems to be this outlet's working okay. Oh! Well, hello there! I'm here to answer part 2B. The reason why the balls did not return to their initial height is because the energy is transformed into the ground, and because of air resistance turning into heat energy, the balls just...
This is part 1B.
Come back up. Part 1B, sorry. Thank you.
Alright, this is part 2, and we are going to show the conservation of momentum. Now, please place the ball here. We have all these balls lined up. This ball will have momentum, and it's going to transfer the momentum to this ball, and successfully each ball after that, and eventually we'll see it transfer to the end ball, which will roll away. So as you can see, most of the momentum from this ball is transferred all the way to this ball through each ball, through each one to the next one. And these balls did move a little bit, so they got some of the momentum, but most of it was transferred to this one.
Oh, wow.
And in that way, momentum was conserved.
Oh! Well, hello there. Well, as you can see, we got an F-150 and an Audi A6, and because this truck sits higher than the A6 and has a different center of gravity, and this car is lower than ground and has a different center of gravity, this car would handle better and accelerate better through corners and have a much better drive than the truck, which would be spinning around the corners more often.
Convince me to buy these.
Oh, well, this price tag is much higher than this, but they both have all-wheel drive, which is good for the snow and Vermont conditions, you know.
Get back to the physics now. Tell us more physics.
What else do you want to know about physics? In the last video, every time I said center of gravity, I meant to say center of mass. My apologies.
Why, hello. When I was picking this up, at any point it was moving, I was doing work. When it stopped moving, I no longer was doing work. But now there's a potential energy because of gravity. If I was to drop this, I'm now using that into kinetic energy. To calculate work, it is force times change in position. Thank you. To calculate power using work, you first need to calculate work. I am exerting work onto this. In order to calculate your work, you first need to find the mass of the object in newtons, and then multiply it by the change in position, which would be the distance from the floor. After you figure that out, you need to divide that by time in order to figure out your power. The one I just did was the actual part 4, not the one that I did before that one.